In this video, we're going to look at the block diagram representation of LTI systems. Just as an introduction to block diagrams are a way to represent a system using interconnections of smaller subsystems, which represent basic mathematical functions. Here are a couple of examples. In this one here, we can see that we have an input over here, x, the output of the system is over here, y. And within the side of the system, we have a couple of mathematical functions. Here's a block that does differentiation. So this would be a differentiator. Here is an adding or summing block. And then this is just a simple multiplication by a constant. In this case, it happens to be negative a. In this example here, you can see we have an adder. We also have an integrator, a block that performs integration. And then we have another multiplication over here. So block diagrams illustrate the flow of signals through the system. So, in these examples here, you can follow the input signal. For example, x coming in here goes into the differentiator, and it also splits off and gets multiplied by negative a. And then those two signals come together and are added to form the output. So the block diagram is a nice way to see how the signals flow through the system, or the subsystem in this case. Block diagrams are useful for designing more complicated systems from simple basic elements, and that's one of the things we're going to do in this video. Also, block diagrams are convenient for computer simulations, something that we will not be doing in this video. So we've seen before that many LTI systems have rational transfer functions. That means the transfer function h of s is a ratio of polynomials in S. So for example, look at this one here. We have some sort of polynomial in S for the numerator. We have another polynomial in S as the denominator. And we can factor both the numerator and denominator. When we factor this, what we end up with on top are terms that contain the zeros of the transfer function, and the denominator contains terms here that are the poles, that contain the poles of the transfer function h of s. So in this, the way it's drawn here, we see that the b's, b1, b2, and so forth, are the zeros, and the a coefficients here, the a numbers, are the poles of our transfer function. Now, we can take h of s and we can write it in a couple of different ways. One way is called the product form, which leads to the series configuration of a block diagram. So what the product form is we take our factored transfer function right here, and we break up each term and simply multiply those terms together, sort of putting them in series like this. So you can see the denominator terms. The 1 over s minus a1 is from this term. This s minus a2 in the denominator leads to this term here, 1 over s minus a2, and we would continue as needed if there are more terms. And then for the numerator terms, we simply have s minus b1, you can see that's written here, s minus b2, etc., etc. So when we write it in product form like this, this directly leads to the series configuration of a block diagram. And so what you see down here is each one of these subsystems, these yellow boxes, refers or corresponds to one of these terms of the transfer function. So there's a direct way to express the transfer function here in terms of a serial or cascade architecture of the system. Now there's another way to write the transfer function, and that is we can write it in what's called summation form. And to do this, we're probably going to have to do partial fraction expansion. And this is going to lead to the so-called parallel configuration of the block diagram. So for example, shown before where we have our factored transfer function here, if we were to perform partial fraction expansion, we can break up this transfer function into a bunch of different terms that are added together. And of course, we would have to determine what these partial fraction coefficients are, the a1, a2, and a3, but we know how to do that. We've done that method several times in the past. So this form here since all of these terms are now added together, right? This is summation form, not product form. We're simply adding the results of these together in the block diagram. So this leads to the so-called parallel configuration. Again, each term in this parallel configuration here refers to a subsystem based on each term in the transfer function up here. So you can see all these subsystems are configured in parallel, and notice they're all added together with a single adder up here, and that's the operation of adding all these terms together in the transfer function. So whether we use the series architecture, which is shown again here, or the parallel architecture, shown again here, we can see that in either case, any system that has a rational transfer function can thus be represented by using just two basic subsystems. And those two subsystems are shown here. The one type is where we have 1 over s minus a, right, where a was happened to be a pole. Right, we see that here and here. We see that in the parallel configuration in these subsystems here. And then the other type of subsystem we need is just has a transfer function of s minus a. And we see that type up here where we called them the B coefficients. Those were the zeros of the transfer function. So our next goal is going to be to realize or figure out how to build these two subsystems, because if we can do that, we can, in theory, then represent any type of system with a block diagram. All right, so let's take a look at our first subsystem basic building block. This is the one where we need to figure out how to make h of s equal s minus a. So if we think about the transfer function for this building block right here, h of s, we know that h of s is defined as y of s over x of s. And that, of course, we want to be equal to be s minus a. So what we're going to do here is something that's called system algebra. So the first thing we can do here is we can multiply this term here and the term on the right by x, by uppercase x here. So we end up with y equals x times s minus a. We can then distribute the x inside the parentheses there, and we get y equals sx minus ax. At this point now, we're ready. We can take the inverse Laplace transform of this expression here to get a differential equation. So y, uppercase y, just becomes lowercase y when we go to the time domain. Remember that s in front of a Laplace transform refers to a derivative. This is the differentiation property of the Laplace transform. So sx becomes dx dt. And then a times big X just becomes a times little x when we go to the time domain. So here's a differential equation that describes this basic building block up here. At this point, we've done this many times before in this course. We can draw a block diagram of this differential equation. Notice that the output y is equal to two terms. It's equal to dx dt. So we're going to have x coming in, going through a differentiator, ddt here, to produce dx dt. And we need to add to that, or actually subtract, a times x. So we're going to take x, bring it through here, multiply it by negative a, and add that to the derivative of x, and that gives us our desired output y. So here, what we've done now is we have this basic building block, s minus a. Any term in the transfer function that has s minus a, we can realize with this block diagram here, consisting of a differentiator, an adder, and a multiplier. Let's go on now and take a look at the second basic building block subsystem. This is the one that has a transfer function, h of s, equal to 1 over s minus a. So we'll start with our transfer function here. We'll rewrite it here. And we could proceed just as we did on the last slide and do the system algebra, but there's actually another method that sometimes is much faster to do, and that's to use the inspection method, which we covered in previous videos. So by looking at this transfer function, I can immediately write a differential equation that describes it. Remember, on top, that refers to the right side with the x's. So the 1 here just means we have an x by itself. Down on the bottom in the denominator, s, these are the y terms now on the left side of the differential equation. The s corresponds to the first derivative of y, dy dt, and minus a gives us a minus ay. So once we have this differential equation, we can actually solve for y. So we're going to solve for this y right here. So to do that, there's a few steps that I didn't show here, but it's just simple algebra. We can bring the ay to the other side, and we can divide everything by a, and we get this equation here. And this can be realized again by using a block diagram. You can see that we're going to need a differentiator, we're going to need a multiplier, and we're going to need an adder. And so when we're all done, here is the block diagram over here on the right for this subsystem right here, which is 1 over s minus a. Now there's another useful form of our result on the last slide. If you remember what we just did on the last slide, we ended up with a block diagram consisting of a differentiator. Sometimes it's desirable to use an integrator instead. So we can easily make that change. So if we start with our differential equation that we got on the last slide, dy dt minus ay equals x, what I'm going to do is, again, I'm going to rewrite this. I'm going to put the derivative term dy dt by itself on the left. I'm going to move this ay over to the right side. And then we can do a little trick here. We can multiply through every term by dt. All right, and once we do that, we get this equation here, and we simply integrate this equation. So dy, when we integrate it, just becomes y, and we're going to take the integral of all of this stuff on the right side, and that's shown here. So once we have this, we can rewrite or redraw our block diagram. This time, notice that y, the output, is expressed not as a derivative, but it's expressed as an integral of x and y. And so that's shown in this block diagram right here. This block diagram consists of an integrator right here, a multiplier, and an adder, and put together in this fashion, this makes the subsystem with a transfer function of 1 over s minus a. All right, let's finish up this video with an example. Suppose we have a transfer function for a system given by this here, h of s equals 1 over s squared minus 1. We're asked to do two things here. Part A, design the system with a series architecture using integrators. And part B, redesign the system with a parallel architecture. All right, so let's go ahead and do this. So for the part A solution, remember that the series architecture means we need to put the transfer function into product form. So the way we do this is we're going to take h of s, given up here, and we're going to factor it. So you can notice this is the difference of squares, s squared minus 1, factors to s minus 1 times s plus 1. And we're going to write this transfer function as a product of two terms here. You see I've split the two terms and they're multiplied together. Now recall from the last slide that whenever we see 1 over s minus some number a, we can replace that term with this block diagram here, which this is the integral or integrator version of this particular subsystem. So we have the product of two of these. Notice in this first one, a is equal to 1, and in the second term, a is equal to negative 1. So we just take this subsystem right here, and I've copied it down here. Right, so this is for the first term. You can see down here this box with a 1 in. Basically, that does nothing, right? We could even eliminate that box if we wanted to. And that's this term right here. The second term, 1 over s plus 1, is this block diagram here where a is negative 1. That's why we have the minus 1 in the box there. And notice these two subsystems, which I've circled here with the blue line. These two subsystems are in series. One after the other. All right, the second part of this example, we were to draw the system using a parallel architecture. So recall that parallel architecture means we have to put the transfer function in summation form. So we're going to start with our transfer function in factored form from the last slide right here, and we have to now decompose this using partial fraction decomposition to write this in summation form. So we would split up this denominator into the two terms here, a over s minus 1 plus b over s plus 1. And these two coefficients, a and b, have to be determined using the methods of partial fractions, which I'm not going to show here because you already know how to do that. But when you do the algebra there, you'll get 1/2 for a and minus 1/2 for b. So we can take those, notice they both have a 1/2 in it, we can take those and bring them out in front. And we've got the transfer function now written in summation form. So again, using the results from the previous slides, whenever we see 1 over s minus a, we can replace it with this block diagram here with the integrator. So you can see we've got two of these terms right in here. One has a of 1, that's this one, let's see, that's this one, and the other has a of minus 1 here. And so now we're going to redraw this system using the summation form, which gives us a parallel architecture. We've got two subsystems in parallel. Notice they're added together. Their outputs are added together here with an adder. And this minus 1 here is needed because remember we have a minus sign for these terms here. Okay, they're actually subtracted from each other. So this one's going to be multiplied by minus 1. And also you can see I've taken the 1/2 here. Each term had the common factor of 1/2. I put it over here in the input, so everything gets multiplied by 1/2 going into the system. Equivalently, you could take that 1/2 and you could put it in the output as well. It doesn't matter where it is. But there is our parallel architecture for this system.